recording. I can see the red thing on top.
Okay.
Yeah. Okay. Now Teams is recording.
Is session 2 of this tutorial session on computational continuum mechanics. So during this week, we would be reviewing the week 2 of the course, which is essentially a tensor and tensor algebra. Yeah, so I mean, let's keep it in a discussion format. I think that would be worthwhile. Like essentially, we start with we'll just be following the same. The thing is, just reviewing them whatever was discussed during week 2 of the course. So we'll start with. I think there is some issue here. Okay, we'll just start with. First of all, we start with vectors.
You're not presenting anymore. I don't know.
Okay. Okay, is that?
Yeah. Right.
Yeah. Okay. Okay. So what we'll do is we'll start with what is a vector. Essentially. In general, I mean, what this course has followed is essentially they should start with tensors, then go to vectors. But I mean, the professor started with vector itself. So I think I'll just change the format here. I'll just start tensors first. So tensor has certain properties in general. I mean, it's essentially a mathematical object. And it has certain properties. The first property is that it's invariant with respect to coordinate systems. And then it has certain properties such as we have some certain properties. Okay, so in general, we denote tensor by a bold-faced letter. Obviously, here I cannot do that, so I'll just be denoting it with say what do you call? So say we have a tensor, tensor A. So if we have a tensor A, then we define the rank of a tensor. So in the sense that let's just consider. Say we take a Cartesian notation. So let's just consider for our explanation purpose Cartesian coordinate system. So in that case, we can represent this. Say it's any general tensor. It's any general. So let A be any nth order tensor. Or sometimes we can just call it nth rank tensor. Yeah, but so in Cartesian system, say if it's an nth rank tensor, then the components of this tensor A will be defined as A, I, J, K, L, and it will go up to say n number of indices. N number of indices. This is the most general representation of a tensor. Now what we do is let's consider it. So when we have just say when we just have one index, so we have say a tensor A, and it has say it has one index. Then it implies that it in Cartesian notation the element is just AI. However, if it's a one index tensor, then there is also known as one rank tensor, and this is what we call as a vector. Okay, and usually the vectors are represented in terms of lowercase, say small case letters, small case letter. And then say then we'll be referring to any vector as say small, say a vector B, C, something like this. We'll just we'll be just be calling it. Now, now since in initial form we'll have say we have we'll call it as a here, and I boldface. So usually I'll just take A with an underline. Now in Cartesian notation, the element or the component of this vector A will be something like AI. Now I can go from 1 to say M, or 1 to D. Now D here represents the dimension of the vector. Okay, now let's start with vectors as to what all properties it has, and essentially say in general we usually tend to, in mechanics and all, since any solid object or any object per se exists in three-dimensional space, so D takes a value of 3, such that any vector A will just have three components. Okay, and at the same time, let me also introduce to you the concept of second order or second rank tensor. So usually the second rank tensor it will have in any reference system, it will have two components, say A and J, and it's usually written in boldface uppercase letter. Okay, so so the representation in any particular reference system will be just it will have two indices, and based on the dimension of the problem, the value of I to J can go from 1 to D, which is the dimension of the problem. So again, in mechanics, we usually tend to, well, most of the problems are always in 3D, so the indices go from 1 to 3. Okay. So now let me just write some, before going to higher order tensor, let's just write some rules of certain rules about representation. Now there are two ways of denoting a tensor. We write in two different ways. There is one what we call as direct notation. In direct notation, we just denote a tensor or any tensor by just a bold-faced letter. Say this, but I'll be using underline just to denote. Even for the second rank tensor, I would be writing a double lines below, double bars below it. And for direct notation, what we do is we just the representation of a tensor. This is how we do it. It's also known as an invariant representation. Invariant representation. This particular representation of a tensor does not depend on any coordinate system, and it represents certain physical properties which are associated with a physical with any physical object. It could be mass, velocity, acceleration, which is essentially intrinsic to that particular body. And the thing is this quantities, but for any mathematical operations, we actually need to convey this or to represent this tensor in a form which makes it amenable to computation. And there is where the need for indicial notation comes. So all the operations on a tensors are done in indicial notation, but since we had I had just mentioned before that tensors are invariant with respect to coordinate system, but to perform any operations on a bunch of tensors, we always need to first represent that tensor in some coordinate system. And such that now, say, for all purposes, we would be using Cartesian coordinate system. Cartesian coordinate system. And the reason why we use Cartesian coordinate system is because it has the simplest, I would call it, the simplest set of basis vectors. And above that, it's considered to be a canonical basis. Because of its simplicity, we just call it a canonical basis. And this coordinate system is what you must all be familiar from, which all of us are familiar from our school days, in the sense that say when we draw a Cartesian system, say this, I'm just taking a 2D Cartesian system, and we have x and y coordinates, this being origin. So what we do is this is a 2D system. Now what we do is we associate x to, and in a set of something like in terms of indicial notations, we'll just call x as x1 and y to be x2. Now this gives us that any coordinates in this particular frame will have x1 and x2 as the location of a point which lies in this particular Cartesian plane. And now what we have here is that we tend to associate direction vectors to both x and y. So x-axis is denoted by I hat, and I hat is a unit vector. Now I'm already jumping ahead, but I'll tell you what we mean by unit vector. And y-axis is just to give you a familiarity with what we have learned during our school days. This is denoted by j hat, and it's also a unit vector. Now here we'll just make a slight change to the just the represent. I mean just the notation part. We'll call I hat to be e1 vector and j hat to be 2 vector. Now you see that. So all the canonical bases in general for any dimension will always refer to as, so the canonical basis is represented always as say e1, e2 till en. Okay, now you'll ask, okay, but the thing is, why is it why it's considered to be the standard, and why is it the simplest set of basis vectors? Now the thing is, since E1 is based in Cartesian space, so in matrix representation, or what we had okay, so we're talking about why do we select canonical basis? What are the advantages of the canonical basis? The thing is, say if you are working in 2D, just as an example, in 2D Cartesian system, then the representation of E1 in matrix form is just 1, 0, and E2 is 0, 1. And in general, say if we have an ND, or sorry, D-D Cartesian system, then our say E1 will be equal to 1, and 0 is D minus 1 times, and the last ED vector is 0. 0 is for D minus 1 time, and last entry will be 1. So this is the reason why we pick up why canonical basis is taken to be the Cartesian coordinate system. Okay, now we'll just start with some. So provided that we have understood the two different types of notation. The first is direct notation, although it gives it actually this is the notation by which we denote any tensor. However, it suffers from certain issues such as we cannot perform mathematical operations. So mathematical operations rather mathematical computations cannot be done. Computations cannot be performed in this notation. Cannot be performed. So that's the reason why initial notation system is required. Okay, now let's just start with studying some of the rules of tensor, rules of these indices. So what we call as rules for indicial operations. I'll just call it rules for indicial operations. Okay. So we have something, we'll start with, say, if an index occurs once in any grouping, then the index is called free index. And second, if it appears twice, then the index is called dummy index. And here it simply means that we are carrying out summation. So summation is implied. So these are the two most important rules. Now let's just have some examples to just understand what these rules actually imply. So say we have this operation. I'm just writing an equation. Say we have bi is equal to aij xj. Okay, and I and j actually are the indices which can run from 1 to n. Okay. Now in this, so what we have is we have groupings. So this is one grouping, and the term on the right is just a single component of any first rank tensor. So what we do, what we see here is on the left, on the right hand side here, which is a grouping of symbols, we see that j is repeated. That means it occurs twice. So here here j is a dummy index. Dummy index. And what we see that I occurs once on both sides. So this implies that I is a free index. Now let's just explore this a bit further. Now what does it actually imply? So let me write it down again. So bi is equal to aij xj. And before in the previous slide, I had mentioned that I and j both runs from 1 to n. Now for simplicity, let's take n to be 2. So I runs from ij to 2. Okay, so it means that n is equal to 2. Okay, so free index means that, say we can have, I can take any value. Now let's take I is equal to 1. For this we have b1 and a1j xj. Okay, now I had said that that the occurrence of any index twice means that there is some summation involved. So this means that we are carrying out a summation over j, such that we will allow j to run over all the values it can take. So it means that So j also starts from 1, so it means that we have a11 x1 plus a12 x2. Okay, and okay, so we have now again I is also allowed to run from 1 to 2. However, it being free in nature, we can have, now let's take the second value of I, which is 2. So then we will have b2 is equal to a2j xj. Okay, and again since j can take values from 1 to 2, we'll have a21 x1 plus a22 x2. Okay, so this was just an example, and ultimately what you see is it's nothing but the set of the matrix equation that we have come across several times. So this is essentially a11, a12, a21, and a22. This is x1, x2, and this is b1, b2. So so this is the whole matrix representation of the of this equation. This and this are equivalent. However, what we say is just a compact form of the matrix equation. So this is our matrix equation, and the above is just a compact form. And in this case, what we see is since I and j are allowed to run only from 1 to 2, here writing the matrix equation is also not that tough. However, say if n can take a very large number, 1000, say n is equal to 1000 or n is equal to 10,000, which usually occurs when we are performing full simulations of any say solid mechanics problems or fluid mechanics problems. Then in that case, we won't be actually able to run with our hands, and it's very tedious. So the thing is, this compact form is able to, we are able to write and do any say mathematical, just to get some idea, or to just to get some idea about the properties of that matrices and all. So this compact form is easier to deal with, and that's the reason why we tend to use compact notations. And the summation notation here, or the summation which I had mentioned, is this is also known as Einstein's notation actually. So it's and this is for any indicial operations. However, it was Einstein who introduced the meaning of summation without explicitly using the summation operator, which is this. Okay. Okay, so what we do now is we'll write the other rules as well. So by now we have written down first and the second rule. Now let's write the third rule. So the third rule says that we cannot have more than, we cannot have an index to appear more than 2 times in a symbol, in the same symbol grouping. So which means that we are not allowed to have symbol grouping such as T, I, J, say we have say T, I, J, and X, J, and say we also have say A, J. So this is not allowed. So such grouping of the symbols is not allowed. Otherwise, if we are say trying to represent such summation, then we have to explicitly use the summation operator. Say this is valid, but this is not valid. So here we can, if you use an explicit summation operator, then having three indices or an index to appear thrice in the same symbol grouping is valid then. Now the first rule that we have is that all symbol grouping in an equation must have the same free index. And that we had seen in the previous equation as well, right? Even in this case, that we just had I on the both sides. Now let me just as an example where this rule says violated. Say we have aj is equal to epsilon I jk delta ij plus dij k lm and fi gil. Now you see clear. Let's just go here symbol by symbol. OK, on the left hand side there is just k. Fine. On the right hand side, let's look at the first symbol grouping. In this case, I and j are repeated. So it means there is a summation involved over I and j. So which is uh, but there is k which appears one. So k is a free index. OK, in this case, fine. We can have repeated indices, which means that they are summed out. However, k remains a free index. OK, so this term, this first symbol grouping has no issue. Let's go to the second symbol grouping. In this case, what we see is we have dijklm figil. In this case, what we see is actually it's jl here. So in this case, what we see here is I is repeated, j is repeated, l is repeated. So we have three repeated indices which are I, j, l. However, k and m appear once. OK, so these two indices, k and m indices, appear once. But as per the rule 4, it must not the all symbol grouping in an equation must have the same free index, which means that since only k occurs on the left hand side, on the right hand side also we are only allowed to have k as the free index. So which means the second term on the right hand side violates this rule. OK, so this was just a demonstration. OK, now let's go for the fifth rule. So the fifth rule says that free and dummy indices may be changed without altering the meaning of an expression, provided we do not violate the preceding rules. OK. OK, so let's just try to understand this statement. It says that free and dummy indices may be changed without altering the meaning of an expression, provided we do not violate the preceding rules. OK, just as a demonstration, let's start with our first example here, which is bij is equal to aij xj. So as per this rule, we can change b I to j and j to I. OK, let's first write here. bj is equal to aj I xi. Okay. Now you'll see that this statement is equivalent. It is the same thing actually. These statements are rather, we'll just call it, they are the same. You are, the thing is, in both the cases, we have I and j are allowed to vary from 1 to n. And in the first case, I was our free index and j was our dummy index. In the second one, it's j which is the free index and I it denotes the summation or the what do you call, or the dummy index. So it means that in this by interchanging the variables, we are still able to maintain the same expression. Now let's try to find some example where we cannot do this as lightly. Say meaning of info. Let's try to construct an example. Okay, but as a general statement, it looks like that in almost all the cases, this will always hold. So how do we select an example when we are violating the previous rules? Okay, so let me come up with an example the next time. I think that would be a better use of our time. So, an example. Where exchanging violates the rules, any of the rules. Okay. What we do is let's just go through some of the important tensors. The first is the Kronecker delta. Kronecker delta. So Kronecker delta, it's a tensor with two indices, say lambda delta ij. Now it has a property which is the value is 1 if I is equal to j, and the value is 0 if I is not equal to j. Fine. And this is a very widely used, it is a very, what do you call, powerful tool in a lot of manipulations and derivations that we usually do in quantum mechanics and solid mechanics um, studies. And another thing is you'll ask, okay, just tell an example where it actually you are actually able to get this Kronecker delta. One is when the simplest example is the dot product of the canonical basis vectors. So the dot product of canonical basis vectors is, say we have ei dot ej. This results in a Kronecker delta. The reason being, in the canonical basis vectors are such that when multiplied with itself, it gives us a value 1. So that is the, so now let me just bring out that notion here. Ei dot ei, okay, or just an example, e1 dot e1 is 1. Okay, And so the thing is the way we define our norm. Okay, so the norm is this is how we define our norm. So the root over e1 dot e1 gives us 1. And this is what we mean by unit norm. And the second quality that it has is, or the second property that it has is e1 dot e2 is equal to 0. And this will hold for all the other cases. So e1 dot en, e1 dot e3 till say e1 dot en, this will always 0. And which implies that they are orthogonal. Okay, so they are orthogonal to each other. And likewise, this unit norm occurs for every indices. So it may also occur for E2. It will also occur for E2 dot E2, and likewise for En dot En. And there is where we see that we observe one pattern here, that if the dot product is taken between two canonical basis vectors which are not the same, then it results in a value of 0. And if the dot product is taken with itself, then it results in a value of 1. And there is how we are able to have the dot product to be represented in term as a Kronecker delta function. Okay, and now the some of the other like scenarios whether it crops up or where it props up is, say we are taking uh, uh, say let's have the component of a vector x. Okay, so this is a vector x and let its component be xi. Okay, and let's take its derivative with some other component xj. So it means that let's xi by xi xj. Now the thing is, if we have the same, if we are taking the component or derivative of the component with with respect to itself, then it will give a value of 1. So which means that say x1 with respect to x1 gives a value of 1. However, since the components of a say of a tens of this particular vector are not to be dependent on one another, then what happens is if we take say partial with x1 with respect to x2, then it gives a value of 0. Okay, and this will hold for all the other say dissimilar indices on the on the numerator and denominator sides. So which means that again this very much fits the pattern of a Kronecker delta. Okay, so that's why, so if its derivative is with respect to itself, then it gives a value of 1. Otherwise it gives a value of 0. And this is a very, and it becomes much more powerful, say the thing is we understand its value say when we are differentiating a matrix, so the components of a matrix, or sorry, the components of a second order tensor with respect to another component of the same tensor. In this case, what we see is this becomes delta ik and delta jl. Okay, so this is how you see, and this will often come across all these results in our forthcoming classes when we are dealing with deformation gradient and all here. And when we tend to find this displacement gradient, there is where we'll come across the use of Kronecker delta again. Okay, and there is one another tensor which is of much use to us. This is known as permutation or alternator symbol. And sometimes it's also referred to as Levi-Civita tensor. Now this is a third order tensor. And in Cartesian representation, we'll call it as epsilon ijk. And or for that matter, any representation, but okay. So this can take 3 values, +1, -1, and 0. Okay. Now it takes a value of 1 if I, j, k are in cyclical order. Now the thing is, we will allow I and j and k to take values from 1 to 3. And the cyclical order of 1 to 3 means, say, 1, 2, and 3. So this is the cyclical order. So this, let it be I, let it be j, let this be k. So if I, j, k are in this fashion, then it takes a value of 1. And if it's in if I, j, k are in, what do you call it, anti-clockwise. So here also the thing is, let's make it more precise. It should be clockwise order. And in this case is anti-clockwise order. So which means that, say, if you're taking the anti-clockwise route, which is 1, 3, 2, 3, 2, 1, and 2, 1, 3, then it takes a value of 1. Now it takes a value of 0 if any two indices are the same. So it means that we are not allowed to take any combination in which I is equal to j, j is equal to k, or I is equal to k, or for that matter, even I is equal to j is equal to k. So if any of these indices repeat in value, or they tend to be the same, then it results in a value of 0. Okay. Now let's just try to understand. There is one property it has is, if you say, if you are given epsilon I, j, k. Okay. Now if you change the order of the indices, say you have made it as, say, I, kj, then the switching or the switch, I mean this exchanging of the indicial places, what it does, it just changes its clockwise or anti-clockwise order. Okay, so if before it was in clockwise order, changing the places of these indices, exchanging the places of the indices will result in its being an anti-clockwise, because of which there will be a negative sign. It will result in a negative sign before the what you call new interchanged, so to speak, tensor. And however, if you interchange the places of two tensors, so if you do this interchanging twice, then it will still have the same thing. So it means that if once you have changed it again, so it was before it was minus, now it will result in one more minus. So -1, and it was minus here. So this becomes epsilon kij. Now what you see is, if the interchanging is done twice, it does not change the value of the tensor. Okay. Now this alternated tensor has a very important role when taking cross product of two vectors. In indicial notation. There is where we see this, we see its importance coming into the picture, or when it actually helps us a lot to simplify the process. Now say we have vector A and vector B, and we are taking its cross product, then this is equal to epsilon ijk aj bk and ei vector. Now here, as per the rules of our indices, what we see is j is repeated and k is repeated, which means that there is a summation involved over j and k, and even I is being repeated. However, here essentially we are essentially the thing is there is this vector also involved, because of which the end result is also a vector, which is say some c vector. Okay, and there is one relation, or what we also call as epsilon delta identity, between Kronecker delta and permutation symbol. And this identity is written as say epsilon I jk and epsilon I lm. This is equal to delta ji rather what we do is we pick up the first indices here, jl. Okay, so it is delta jl and then km, delta km minus jm, so delta jm and minus and delta kl, and this is an identity which the thing is this can easily be derived, but however it comes in handy. This particular simple form comes in handy a lot. Okay, now what we do is let's just do some examples on this solve problems for this. I'll just use our solve problems part. Okay, so the solve problem, let's solve a couple of problems here. Let's start with a simple example. So the divergence of x vector is what? Now before that, let me first introduce what we mean by this delta operator here. So delta operator is nothing but partial of partial xi and something operating and then ei vector. And since there is a summation involved, it simply means that we can write this as delta or delta x1 some argument and then e1 vector plus x2 some argument of e2 some argument then e2, and then the third term is x3 some argument then e3. Okay, and the divergence here simply implies that what we do is let's write this let's start this in indicial notation. So let's call this delta by delta xi, and I'll just write ei before here, and then this dot xk, or rather maybe just xj and ej. Okay, now what we do is let's do this delta xi and xj will be goes as an argument for this operator. This is an operator, and here we'll have ei dot ej. Now you recall from our from the definition of our so now we recall from the definition of our Kronecker delta, this comes out to be delta ij, isn't it? So it means we'll have And here also what we have is this operation also leads us to delta ij. So what we have is delta ij and delta ij. And here, and there is one more property of Kronecker delta, that I and j can be interchanged. Okay, so even so delta ij is the same as delta ji, right? So that is an important property of Kronecker delta function. Okay. So now let's discuss that why does this occur. So now what happens here is, so there is a summation involved over both I and j, and you know that I and j both can take values from 1 to 3. So what we do here is we have something called as let's try to expand this. So this will result in 9 terms. Okay, so let's just do it for the sake, right? Okay, just to understand. So say now we'll keep j fixed and let I vary. So we'll have delta 1 1 delta 1 1 plus delta 2 1 delta 2 1 plus delta 3 1 delta 3 1. Okay, and plus delta. Then we'll have j is equal to fixed to be 2. So we'll have delta 2 delta 1 2 and delta 1 plus delta 2 2 delta 2 2 plus delta 3 2 delta 3 2. Likewise, we'll have delta 1 3 delta 1 3 plus delta 2 3 delta 2 3 delta 3 3 delta 3 3. Now let's use the properties of delta function. Okay, so we'll have delta 1 1 is 1 and delta 1 1. So this gives as a 1. However, you see the delta 2 1 delta 2 1. So if the two indices are not the same, that the result is 0, right? So this is 0. This is also 0. Likewise, this is also 0, and this is also 0. Here also this is also 0. So we are left with 3 groups, delta 1 1 delta 1 1. So essentially we have 1 into 1 plus 1 into 1 plus 1 into 1, and this gives us a result. Now we could have used a simpler form, I mean the delta property itself. Now what delta also has a property that say it's also called as a substitution property. So say uh, so what happens is, if delta has an index which okay, let me try to explain it using a simple example first. So if you have, say, delta ij and xj, or delta ij and uj, then what happens? What you see here is delta has an index which another term also holds in the same symbol grouping, right? So what you can do is delta will just replace the repeated term with the other index it has. So it will be this. This gives us ui. Okay, so it means that if j is repeated, j will be replaced by 1. So this is known as the substitution property of delta. Now let's use in our problem here. So we have delta ij and delta ij. Now in this case, what you see is I and j are both repeated. However, what we do is let's just focus on I here. So I is repeated, isn't it, in both the terms? Sorry, in both the deltas in the same grouping. What we do is j is repeated. So what it will do is let it replace j with I. So this will be delta I. And you know that if the if the index appears twice, then simply means that there is a summation involved. So this is equal to lambda 1 delta 1 1 plus delta 2 2 plus delta 3 3, and this gave us 1 plus 1 plus 2. Right? This is much neater version, right? Rather than going through this detailed process, we just use the substitution property and get the value of 3. So the answer of divergence of any vector x is 3. Okay. Now, what we do is we have defined the second order tensor, isn't it? So that is done. And there are certain properties which, since they are properties, I think we should just we should rather solve the examples corresponding to that. I believe since the properties are something which you just need to revise again and again. So let's just solve some say some problems with where we have second order tensor. Okay. Before that, what we let me do is let me just introduce the concept of dyad product. I think dyad. Okay. So what we do is, so dyad product. So say we are given two vectors which are u and v. The dyad or tensor product is defined as, in direct notation, we define this as u1 v. This can also be pronounced as bun. Okay, so you call this symbol as bun. I learned this during one of my classes that I did here. And the initial notation is ui vj. Fine. And we also have something called a matrix notation. So provided that you have represented u and v in some basis, which we usually will take it to be the standard basis, this is the Cartesian basis, then it can be represented as u into v transpose. Fine. Okay. Okay. And what dyad product does is it increases the rank. Say if you take a dyad product of two vectors. So say dyad product of two vectors gives us a second rank, or you can say that second order or second rank tensor. Okay, which in our case we'll just call it in our scenario we call a second rank tensor to be tensor and first rank tensor to be a vector in our studies here. Okay, so what you say is if you have two vectors and after taking dot products, you are actually increasing the number of indices the resultant quantity has, right? And that is what dot operation, and that's why we often call this dot product to be also tensor product. Okay, there are some properties which this dot product tend to have. So say you have say you have a dot product U1V and you operate this on W. W is another vector. Then this is equal to W dot V into U. So when you have operated a dot product on a vector, it results in a vector. Okay, and this is the form of the operation. Now in indicial notation, it will have the effect as if you have UI, Vj, and Wj, then this is the same as Wj, Vj, and Ui. Okay, and this is in the indicial form. Now what we do is let us use this property. Let's just use this property of a diode. Okay. Say in solving one example. Now let's do it as an example, separate example here. So the question is show that A U1 V is the same as A U1 V. Like this. Let's try to solve this in indicial notation. Okay, so you start with say A can be represented as in terms of Cartesian notice in terms of Cartesian reference system is AI Ti 1 of. So in any tensor can it be represented in what do you call in any particular coordinate system as something of this. So in this case, since it's a second order tensor, we'll have ij and ei1 ej. So it simply means that the number of indices has the number of combinations among the basis vectors of that particular reference frame there will be. Okay, and we'll call say ui sorry u vector to be uj, rather not j but say uk ek, and v vector will represent it as VLEL. Okay, so now let's start with the term on the left hand side. So A U1V. So this will be can be written as AIJ EI1 EJ and UK EK 1 VLEL. And then what you'll do is let's bring all the terms so that we have AIJ UK VL, and then let's do something called EI 1 EJ, and this will be acting on EK1 EL. Okay, now on this, so the thing is on the either sides of the 1 operation. So say if what do you call, if this operation goes as if if uh, say bun is acting here and bun is here, right? So the for the bun on this case it's ej and in this case ek. So we see that there is there is nothing explicitly going on here, right, between these two. So based on the property of diode, what we had seen is, so on the what do you call on the side of say if a diode is acting on some quantity, then the side at which that operation is being done, that act of that diode is going on, that side actually becomes a dot, isn't it? So actually the thing is, this is the same as u. I'll just clarify this. This is the same as you have u and you have v on the side of the vector which is being acted upon. So that converts into a dot product. So just notice the pattern here. We are going to use this. Likewise here, diode is acting ei bun ej is acting on ek bun el, right? So it is this action which is, so these two terms, there is, it just converts into a dot product. That's what I'm trying to say here. So it will be all the formulas aij uk vl, and this becomes ei. Okay, then it will become ei ej dot ek, and this bun still remains el. Fine. So there is a very sophisticated thing going on. So you should, this is a very tricky situation. So you should just look at the pattern here. So this ei dot ejk ak is nothing but the Kronecker delta, which is jk. Okay, so what we are left with is aij uk vl and delta ij delta jk, and you have ei bun el. Fine. Now let's use the substitution property of the Kronecker delta. So here you see where is j and k are both repeated, right? J and k are both repeated. So what we'll do here is, let's just we can use let's take this two terms. So in this case, k is being repeated, right? So what it will do, this delta operator will do is, delta will just substitute k with j. So this becomes aij uj vl ei cross. Fine. Now here is one particular beautiful thing happening. And let me write on the sideways here. Now when you have A acting on VU, then it's nothing but Aij, Ej, Ek, Ej. This is acting on U. Yeah, U, and let this be honest. Say U, K, Ek. Okay, and this will be Aij, E, and then we'll have UK, and then this one will be EI, EJ dot EK, and this becomes AIJ UK EI delta JK, and we'll use the same substitution property such that it becomes AIJ UJ EI. Now you see that commonality here, right? This is the same as this. So this one we can just what we can do is, let's try to slightly change the places. We'll have AIJ UJ EI, fine, and Bunny of VL EL. And what we just saw is this operation is this and this is the same. So this you can write as A acting on U dot product with V. So this is what we have shown, what we had actually wanted to show here. Okay. Now let's proceed to the another part here. Uh, solve some problems. Now let's furthermore in this sequence, right? So let's show that I'm sure having that done the previous tough problem, this will be a much easier problem to solve. This is equal to EI dot EA, where A is a second order tensor, or what we here is just a tensor. Okay. Now here what we do is let's represent the tensor A as A KL EK dot product with EL. Fine. And this one will be, then what we do is let it act on EJ. So this gives us AKL EK EL acting on EJ. Now we'll use that property here. We'll have AL EK and EL dot EJ, such that we have EKL and EK, and then this becomes delta J. EK and this becomes delta LJ. Now what you see here is L and L is repeated, isn't it? L is being repeated. So what it will do is it will just substitute that with what the other index that del has. So this becomes A KJ EK. Fine. Now when we take EI dot A EJ A EJ, then this becomes taking EI dot AKJ EK, and this is the same as EI dot EK. This we have AKJ delta IK, and again using the substitution property of delta, this becomes A IJ. Now you see, right, we are able to show whatever. So this implies that AIJ is equal to dot AJ. Or just leave this. Fine. So it seems that let's just review further some of the more what we call as the invariants. So vectors and tensor invariants. Okay. So there are what happens is there are certain properties of a tensor or a vector which doesn't change even if you change the coordinate system, even if there is a transformation of the coordinate system. Okay. Now, as you may just I'm just before that, let me just give a brief overview of what is just a summary of the transformation operations. So what we call as transformation rules. Okay. Now you say uh, uh, say you have a vector v. Okay. Now suppose that you had some representation of v in terms of Cartesian coordinates as say v I e I. I'm just using the summation implied rule here. Now say this coordinate system ei is going through some transformation in the sense that let me write in 3D. Well, let me just give you a schematic of what's happening here. Say you have this Cartesian system E1, E2, and E3 undergoing some arbitrary transformation such that E1 prime becomes this and E2 prime becomes this and E3 is E3 what do you call coordinate E3, yeah, the E3 unit direction becomes this. Okay. So E3. So which means that E3, E1, E2, E3 set of the set of basis vectors that were define this Cartesian's 3D Cartesian space is going to get transformed in such a manner that there's some what you call operation. After applying some operation, it's resulting into after some rotation, right? It's becoming it's giving rise to a set of bases E1 prime, E2 prime, and E3 prime. And this prime, how we denote this is denoted as say E I prime is given as Q K I and E K. Fine. So this is the transformation rule that's going on. Now when we write say we have this coordinate system, I mean the representation of a vector v in terms of Cartesian as v I e I, then after and then let's just give it some matrix. Let's call it this to be the representation v1, v2, v3. Now after because of the and this let's just for now denote as v itself. Okay. Then because of the transformation of the what do you call this Cartesian axis coordinate system, then the new components will be v this let it be the new components in the new transformed coordinate system, and this is related by q transpose, and this qx is a second order tensor, right? Or what you call as tensor here. So this is the relation. And for a matrix or for a second order tensor, or what we call here in this particular study as tensor, then this after transformation the representation will have this coin. Okay, so these are the rules that I want to specify here. Now, so there are certain quantities which are invariant with respect to the transformation. So this is what we are going to take a look here. for a vector, or rather for vectors, the rule, I mean, the thing that is preserved is dot product. So one of the things that is preserved is dot product of two vectors remain invariant under change of axis. Fine. Now I'll ask me why. Just let me show you. So say you have vectors u and v. After getting transform, or sorry, under a new transform coordinate system, the components will be say u prime as the component set will be u prime and v prime. And u prime is given as q transpose u and v prime. And again, I forgot to mention that q here is a second order tensor that is very much understood from the context and from the definite from the it's very clear. It has certain properties. It has the following properties. Now it has the following property that q transpose q is equal to q following properties q transpose is equal to identity, and the second property is that q inverse is equal to q transpose. It's actually the second property which results in the first, or vice versa. I mean, it's the same thing. Yeah. So this is what we call as orthogonality property, and this which means that q also is also known as orthogonal tensor. Fine. Now we again here transforms as q transpose v. Now when you take dot product of u transpose or v transpose, what you see is you'll have q transpose u dot q transpose v, and you could use it is that property. There is one property here which is of a second order tensor, that this becomes u dot q transpose q transpose v. So this becomes u, and transpose of a transpose is the metric, is the tensor itself. So q transpose v, and this you very well recall its identity tensor. So this becomes u dot iv, and identity when it acts on a vector keeps the vector intact, so you'll have just u dot v. So you saw that the dot product remains invariant under transformation. Okay. Likewise, there are some other certain for tensors. There are some invariants. What you have is that the trace of a tensor. So I'll just try to say, given a tensor A, there are certain invariants associated with it. The first is trace of A transpose. Trace of A is nothing but the sum of the components on the diagonal is constant even after transformation, and then there are certain other what you call the second and the second is the double summation or the double contraction of two of the what you call of the tensor with itself is also constant, and this is the first invariant, second invariant, and the third invariant is that the determinant of a tensor is also constant. So these are the invariant quantities for tensors. Then we have eigenvalues and eigenvectors. Yeah, so I think we are pretty much done for the day. And so what we do is, I believe that only if you have, if you have problems to solve, then it will be more worthwhile to discuss further. Otherwise, I think the text in the course content is what they call is complete in itself. So what I will do is I'll just close the session for today, and let's discuss it in the next. Let's discuss the if you have any problems, let's discuss in during the next tutorial session. And I think this would be enough for today. Okay, thanks. Yeah, and we'll meet on 15th of August. Despite it being a national holiday, we'll still have a short discussion on that. Thanks. Yeah.